Okay. Last time we did, so I said there were 4 types of triangles. One was the angle, side angle, or rather, for any given triangles, the types of problems that we're working on is where we have 3 unknowns. These are either sides or angles. And then we're trying to find the other 3, because every triangle has 3 angles and 3 sides. So you could choose any 3 of them and from that get all the others. And so last time we did angle, side, angle, and angle, angle, side. We did the angle, side, side, which did your homework prove that this was a pain in the angle, side, side? Was it? Yeah, it is. It definitely is. Now there's 2 other kinds. And so these we could take care of with the law of sines. The other 2 types, we are going to use the law of cosines, abbreviated LOS and LOC. And so these other kinds are side angle side and side side side. Okay?
Wait. Oh, side.
Now, are you looking at this and thinking, what's the difference between that and that? Or wait.
That and that.
That and that, yeah, rather, that and that. So the difference is, and the reason it's written like that, is because the angle is between the 2 sides. So side angle side would be where you're given, let's say if you're given an alpha, then they also give you B and C. Or if you're given, say, we'll call this gamma, you're not given C, you're given, say, A and B.
Yeah.
Now, the difference there, and why the, I was about to call it that, the reason why the angle side side is different, angle side side, is that crucially here is that the given angle, right, that let's say if this angle was given, one of the sides that's given has to be the opposite side. So if alpha was given, A would have to be given. In this case, gamma's given, then C would have to be given. Yeah. Okay. So crucial difference here. You cannot do a side angle side where you have these 2 sides with the law of sines. How are you going to do that? There's no opposite side here. That's the thing you're trying to find, right? And so with angle side side, well, we call it that, and it's the side is paired with the angle that's given. You don't have that here in side angle side. And also, obviously, side 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 has no angles, right? That would be something like this, where they give you, say, 5, 20, and I don't know, 18 or something, right? In that case, it would probably have to be 20 and 18, who cares? So there, no angles are given. What do you do with that? Obviously, you can't use law of sines. So what do? Well, that's what we're going to be doing today. It's to deal with these last 2, we use the law of cosines.
What about angle?
Angle,
Well, there could be
angle.
There could be infinite.
There could be infinitely many. Good point. Right? That doesn't uniquely determine the size of... Because let's take 30, 60, 90. What size... Yeah, it could be anything. So that's a good question. You stumped me. Thank you, Noah. I was about to just pull something out of somewhere. Well, you see, we're not dealing with that in this class. You won't deal with that until you get to at least your senior level math, not extra. Yeah. Okay. So, let's do it. So, law of cosines, your book, again, does this proof with a drawing of an obtuse triangle. I'm going to use an acute one just because you could look in your book and see how they deal with the obtuse one. It's going to be exactly the same. And at the end of class today, I will do something with an obtuse angle just so you could, because if you were to just read the obtuse proof in the book, you might go, wait a minute, how is that? There's something there that you might go, wait a minute, that doesn't work. I'm going to address that. So anyway, okay, so let's take a triangle. Okay, there's my given triangle, and it has 3 angles. Okay, or alpha, we're going to call this one gamma, and we're going to call this one beta. Doesn't matter, right? As always, we could have named them anything we want, just as long as alpha's paired with A, gamma's paired with C, and beta's paired with B. So we have this. Any acute triangle. Let's do this. And again, it could be obtuse, and you'll come to the exact same conclusion. We're going to drop coordinates right here. And then we're going to do this. Obviously, from here to here has some height. Let's call it h. Okay, from there to there, just like last time, there's h. Also, crucially, if you were to draw a line right there, splitting that guy into 2 right triangles, so in fact, I'm going to do that with a dotted line. We're going to split this into 2 right triangles, like that and like that. And now, okay, this entire length, I want to be careful here. This entire length from there to there is C. Let's give this length from there to there a name. Let's call it K. Since we used H, now let's use K. Everybody with me on that? Yeah. Okay. Let's do it that way. So now, just like last time, I'm going to take sine of alpha. Sine alpha is equal to what over what?
H over B.
Right, it's the total height. So you could even think about it. If I were just drawing that triangle right there, I would label that length H, right? And so it's H over what did you say?
B.
B. So, and again, I'm anticipating what we're going to do. Eventually, we're going to get this H by itself. So I'm going to go ahead and do that. H is equal to what?
B sine.
B sine alpha. Now, we can do cosine of alpha too. What is cosine of alpha?
K over
Alpha is what over what?
K
C
over.
over.
Wait.
Not C. C is all of that. And cosine, the way we've defined it, only works with that opposite and adjacent and stuff if you have a right triangle. That's why I decided to call that length from there to there K. So what is cosine alpha? K over what?
K over B.
And K by itself would be what?
B times
B times cosine alpha. Whatever cosine alpha happens to be. Okay, so now check this out. I'm going to redraw this triangle right here. This one. This length right there is A, right? Meaning that this is beta. That's half. Well, we don't know if it's half. It's some part of gamma. I'm not too concerned about it. But crucially, the height is, what's the height? H. And what's that length right there?
C minus.
Good, good, right? If that total length is, say, 5, and that one's 3, you'd say, well, that's 2. What would you have just done? You would have taken the bigger length, minus off the smaller length. So let's just call it that. And I'm going to put in parentheses, C minus K. Whatever it happens to be. Okay. But this is a right triangle, yeah?
So
So
we can find the other angle.
we could if we cared. I don't care. Right now, what's going to help us out is to just simply notice that since it's a right triangle, Pythagorean theorem applies. And so the Pythagorean theorem in this case, there's my hypotenuse. So it's going to be a squared is equal to that squared times plus that squared. So we have h squared plus c minus k squared. But that doesn't help us out at all. Like that's not useful given, because remember, we're trying to deal with these guys. And in fact, side, we're not quite there yet. What we're really working on, well, it's going to give us both of them, but we're kind of thinking about this in terms of an angle. Everything we've talked about thus far, everything we wrote on the board was in terms of an angle, so let's get that angle in there. And to do that, I'm just going to substitute. I'm going to say instead of h, right? Instead of h, whatever that is, squared, I'm just going to take that and put in b sine alpha, whatever that is, squared. Now instead of c minus k, this is going to be c minus, instead of k, b cosine alpha. Now, you're looking at that, it's like, well, it didn't really make my life that much easier. But maybe if we multiply some stuff out, maybe some things will cancel and we'll end up with a nice formula. And we will. So, here we go. So I'm going to say, okay, I square this. What do I get if I square that? I'm going to move this over a little bit to give me some room.
B squared sine squared.
B squared.
2b
Sine squared. Hold on, I'm getting ahead of me. Okay, so that is that squared. Now, let's square that, and what do we get?
C squared minus 2b
There we go.
cosine squared.
Minus
b
2, right? Because the inner outer are the same thing. So it's BC, and I'm going to do it in order, in alphabetical order. So it'll be BC cosine, right? Minus another, so negative BC cosine, minus another negative BC cosine. So 2 BC cosine alphas. Now, last is what?
plus
Good job. B squared what?
cosine squared alpha.
Cosine squared alpha. Good job. All right, we didn't need to like write all that out. So now, this is something you always want to look for. If you ever see that you have either a sine of something squared, like it's nice to just look around and see if you have a cosine of the same thing squared, and you do. So that's nice because if we can put them together, and I'm gonna do this explicitly. We have sine squared alpha plus b squared cosine squared alpha plus c squared minus 2bc
Now we can
cosine alpha. Now what can we do?
factor out b squared.
Factor out the b squared. That gives us sine squared of something plus cosine squared of the same thing. That's crucial. If this were alpha and that were beta, then we couldn't go any further. But since they're the same thing, that's just 1. And so this reduces down to b squared plus c squared minus 2bc cosine alpha. And that, at the very beginning, was a squared. So I could have had it a squared, a squared, a squared, a squared, a squared. Now, you can find that length.
And if alpha was 90, then it would just be a squared equals b squared plus c squared.
Way ahead of me. We're gonna talk at the very end about something. So now check this out. Notice I did this with alpha. I could have done this with any of them. Okay, like I could have started by saying, well, let's do gamma, in which case the opposite would have been c, and so on and so forth, right? And so the way I remember, this is just one part of the law of cosines. And of course, this always starts with, given a triangle ABC. So we're starting with some given triangle ABC with the convention that we have, right? With alpha's opposite A, beta is opposite B, gamma's opposite C. We're not talking about a right triangle, though it could be. Like Noah observed, if it happens to be a right triangle, it will reduce down to something that we've already proved before. But here we go. So let's just think about. So I want to get all of them out. So a squared b a squared. You notice this. Just look at how this looks. You know that you have 3 sides in these triangles that we're doing because we're talking about a given triangle ABC. That's the context. Okay. Given that, it's true that whatever side you're looking for, that's the opposite angle is what shows up in cosine. Okay? And so the way I write this down is I start with, okay, what's the side I'm looking for or whatever? Well, a squared. And then I think, okay, then the cosine part goes with the opposite angle to that. Since you're talking about A, it's alpha. And then as for the rest of it, it's just the other 2 sides, right? So it's, since we've used a squared on the left-hand side, I know that it's b squared plus c squared minus 2bc. So let's reason And like, we don't have to do it with each of these and just say, well, if we had started with beta in this place, then b would have been the opposite side. That's the length that we would have had here. So it would have been b squared equals some stuff with cosine beta, and then what would the other bits be here?
A squared plus, yeah, C
A squared plus c squared minus 2ac.
Yeah.
And finally, if c squared were the thing we wanted, then it would be cosine what?
A squared plus B. Gamma.
Did you cosine of what angle?
Gamma.
Gamma, because it's these pair together. And then it would be what letters, or what sides?
A squared plus B squared.
There we go. A squared plus b squared minus 2ab. So this is the law of cosines. So, given a triangle ABC with the usual lettering, these are true. And we don't need to go through and prove the other two, because I mean, come on, this is what we just did. So, okay, now, Noah was ahead of me. Because recall, in lecture 2, I said, I was reviewing the tape last night, and I realized I said something wrong during lecture 1. And what I said, just kind of offhand, I said, if your triangle is a right triangle, given the letters A, B, C, if it's a right triangle, and we proved this in class, I said, if it's a right triangle, then A squared plus B squared equals C squared. Which is true, we proved that. But then, I'm sorry guys, give me just a minute. This is such a pain. Glad I remembered to bring this today though. Alright, there we go. But then we spent a long time that day talking about implications. And so if A implies B, right? So like if Spot is a dog, or if Spot is a Dalmatian, then Spot is a dog. And I said, it's not necessarily true. If Spot is a Dalmatian, then Spot is a dog. That's true. But the other way is not necessarily true. If Spot is a dog, then Spot is a Dalmatian. That does not always work. But I said very cavalier in lecture 1. So we proved that if triangle ABC is a right triangle, okay, everybody got that? This is what I'm saying here. If ABC is a right triangle, then A squared plus B squared is equal to C squared. But in lecture 1, I said, well, we know that A squared plus B squared equals C squared, therefore ABC is a right triangle. And I made this mistake right here. I said, we know that A squared plus B squared, because we were doing something, and I said, oh look, A squared plus B squared equals C squared, therefore, triangle ABC is a right triangle. But we didn't prove that. It doesn't follow from this that that is necessarily true. The same way, if you say, if Spot is a Dalmatian, then Spot is a dog, it's not necessarily true that if Spot is a dog, then Spot is a Dalmatian. But I said, this does actually turn out to be true for a reason that we'll see later. And if you remember, our setup was that C was the hypotenuse, right? I mean, that's what this means. So now let's suppose we have some right triangle. Or we have some triangle, okay? And let's just call this C right here. And maybe this is a, and this is B. So that would mean that that's alpha, this is beta, opposite C would be gamma. And let's suppose that it's true that A squared plus B squared equals C squared. Does that mean that ABC is a right triangle? Well, what we just proved is that given this setup, this must be true. And so, So now we're supposed, and both of these is assuming that you have some triangle floating around, triangle ABC. And now we're supposing that a squared plus b squared is equal to c squared. Okay, so that's our setup. Well now, since this is some triangle, this is true. So it must be the case that c squared equals a squared plus b squared minus 2ab cosine gamma. Okay, then, but it's also true that this is the case, yeah? So in other words, c squared is equal to a squared plus b squared. So a squared plus b squared is equal to a squared plus b squared minus 2ab cosine gamma. Well, that cancels that, and we get that 0 is equal to negative 2ab cosine gamma. Is a equal to 0?
No.
Can it possibly be equal to 0?
No.
No, because then you wouldn't have a triangle, right? You'd have something else. It wouldn't be a triangle. Can b be equal to 0?
No.
No, neither of them could be equal to 0. Is 2 equal to 0?
I don't think so.
I did not. Last time I checked, it wasn't. Now, don't quote me on that. So I could divide by negative 2ab, both sides. And that cancels, and I'm left with 0 is equal to cosine gamma. Therefore, cosine is equal to what?
9. Or gamma is equal to 9.
Or pi over 2, right? So this is cosine. It's equal to pi over 2, which is 90 degrees, right? Or could it be equal to 3 pi over 2?
Yes. But then it just goes this.
Well, it would be bigger than an obtuse angle. That would be, right, like, this would be one of your angles. That would be gamma. And you'd have, that would be your triangle, I guess, right? So, I mean, you could say, well, what about the other side? Well, then you're not really talking, like, the part of this assumption that you have a triangle ABC is that the biggest that any one of these can, none of them can be 180 by themselves.
Yeah.
Right? Because if it hits 180, you no longer have a triangle, at least in Euclidean geometry. Maybe like on a sphere, it's possible, but not on the plane. So we know that your angle must be between, it can't be 0. It can't be 180. So it has to be somewhere in between. For this to be true, it must be that gamma is equal to pi over 2, or in other words, equal to 90 degrees, and therefore, ABC is a right triangle. So in fact, you could say a squared plus b squared equals c squared if and only if ABC is a right triangle. Which means both implications are true.
Yeah.
Which means that they're kind of the same thing. Which is what I said, kind of cavalier, lecture 1, and then lecture 2 I caught it and was like, we haven't proved that. It does turn out to be true, but because of something that we don't have yet. Now that we have it, we could prove it. And so given this setup where you have sides A, B, and C, if a squared plus b squared equals c squared, then it must be a right triangle. Q, E, T. Okay. I just wanted to return to that because I promised that we would. And I know you guys have just been waiting like, oh, is today the day? Are we going to do it today? Okay, so that's all I wanted to say on that. Now, let's actually use a law of cosines to do 2 different types of triangles. And then we'll go into one other thing that we need from this section. Okay, so here we go. Any questions before we move on? Please don't ask me about the hyperbolic trig functions. I'll talk all day. All day. Okay, so here we go. Okay, so here's the setup. This is problem number 8 from this section. And it gives us that beta is equal to 73 degrees, 50 minutes.
So 73 and 5/6.
And 5/6. But we're going to convert that immediately into decimals because we're going to put it in a calculator. And it's going to make our lives much easier. And so C equals 14.0. And A is equal to 87.0. And we want to solve the triangle. This is all of these assume triangle ABC. So beta is opposite B, etc., etc. And now we need to do this. So I'm going to start by drawing this guy. And since beta is the one that I've been given, I'm going to put it in standard position here. I'm going to say, okay, here's beta. Like that. There's beta. Now, opposite from beta is B. And obviously I'm not drawing this well because they all look about the same size. This one's way bigger than that one, but whatever, okay? So I'm going to call this alpha. I'm going to call this gamma. It doesn't matter. A is opposite alpha, so I'm going to write A equals 87.0. It will help you to actually write these out because I'm going to do a bunch of stuff. Then I'm going to put a bunch of things into my calculator. And you'll find, like, if you could just look at your picture and see, oh yeah, that one's A, that one's that. It'll make your life easier. But, you know, whatever. B is the unknown. That's one of the ones we don't know. C, which is opposite gamma, is 14. And I don't need the 0.0 for that. It's just, in the end, since there's one decimal here, the final thing I'm going to write will have one decimal place. So otherwise, like if it comes out to like 1,000,000 decimal places, it's like, that means you've measured like the micrometers, but here they only measured centimeters, or if that, decameters. And, come on. Really? Like, you're trying to get more accuracy out of. It's like using a ruler and then saying, "Oh yeah, that's good down to like the nanometer level." Like, no, it's not. You're estimating here. You're estimating that. So that's just one of those things. Okay, so to do this, we're going to use. Well, first off, let's just pretend that I didn't know. And I'm going to take a look at this and see. Okay, I have given one angle and two sides. So is this the pane in the angle side? And I say, well, the given one is opposite one that I don't know. And so I must be in the case, and then, or you could just immediately notice that your given angle is between two given sides. And right there you know, okay, I'm going to use law of cosines. And the way we're going to do that is, and with this, obviously, since you're going to be using beta, beta is the only one that you have. 73 point some stuff. That's the only one you have. Well, you can't use that. Can't use that. That's got to be the one that you use. And so let's go ahead and use that and say, okay, then it's the case that b squared equals a squared plus c squared minus 2ac cosine beta goes with b. So beta. Okay. Now I'm just going to plug this stuff in. A, and this is what I mean by it's nice to have it all written right here. So A goes, like, and you could look at this, but oftentimes what happens is like you're looking at this geometrically because you know that this pairs with these and that's whatever. So that's just my recommendation. So we have 87 squared plus 14 squared minus 2 times 87 times 14 cosine the 73 point stuff that I haven't figured out yet. That is what b squared is. So I'm going to plug all of that into my calculator in one fell swoop, rather than try to do the cosine, and then I do the 2 times stuff, and blah, 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 blah. It's much easier if I just get all of it into my calculator at once. So that's what I'm going to do. Turn it on and make sure I'm in degrees. Am I in degrees? Yes. Okay, so 87 squared plus 14 squared minus 2 times 87 times 1/4 times cosine. Oh, I didn't do the conversion. Well, I'll just do this all at once.
It's 8 and a bunch of 3.
73. So what I'm doing right now, I'm plugging into my calculator cosine 73 plus 50 divided by 60 end parentheses. That's what I'm putting in. So 73 plus 50 divided by 60. I could have done 5 divided by 6. Altogether, I get 7086.7387. Just like that. Now, I'm going to go ahead and do this. 73 plus 50 over 60. And that gives me, just like you said, 73 plus 0.83 and a bunch of 3. So I'm going to put 3 repeating. 3 repeating degrees. Okay, and that's what I would be using here. And since I'd already calculated it, when I wanted to go plug it into my calculator, I would just go up. Yeah. That way I'm not losing any significant digits. Okay, so, okay, now I don't want b squared. I want b by itself. So what do I need to do?
Square root.
Do I take the positive or the negative square root?
The positive.
The positive, because we're talking about lengths. And in this context, lengths are positive. So that gives me 8.5926. Oh, that's not right. That's not even close to being right. That would be between 64 and 81. Or square it, it would be between 64 and 81, and that ain't right. So what I did is I went up and grabbed the wrong number. So I'm going to go up and grab the right number, which is 7,086 and stuff. Thank you for catching that. Thank you. And what I get is 84.18277. Notice I'm keeping a lot of digits because I don't want to mess around with that. Okay, so that is what I got here when I did it. Okay, good. Okay, now what do we do? I mean, we know that this is, and I'm going to go ahead and write it, 84. And now when my final answer, I'm going to round to the same decimal place. Since this had one decimal place, I'm going to round this to 84.2.
Well, we can, it's like an angle side to side. We can just find.
There you go, right? We could, and so law of sines is what we've been using up to this point. We can set up a law of sines for each one of these. Here's this one and this one. So in other words, sine beta is to be, which is 84 point. And when I do this, I'm not going to use 2. That would be very, very bad. You want to use this that's in your calculator. Or if your calculator's not smart like that, you write out a bunch of these so that you get a more accurate answer than if you'd done it the other way. And we could do this with either of them. We could go with sine alpha over A, which is 87. And so I'm going to do that. And I'm going to go 87 comes upstairs. 87 sine beta over 84.2 is equal to sine alpha. Because I'm looking for alpha, A is already given, right? So I'm going to put that all together. 87 times sine of beta was that, was 73. So I'm going to go up and grab beta, sine beta. Oh, if I didn't have beta, I wouldn't have used it.
Yeah.
Right? Divide by, not 84.2. I'm going to go up into my calculator until I get to the 84.18276.971. Do that, and I get...
0.99.
Yeah.
0.99259810.
Oh, that's because I did gamma last night. Okay, that's fine. I was like, I didn't see this number before. I'm sure it'll work. 0.99259.
Always just barely. The sine of alpha equals 0.99. Why can't it just be 1 and then it doesn't work though?
Right. Yeah. Yeah. Sine alpha, we're 1. Yeah. So this is why you really got to make sure you're using as many digits as possible. Because it's possible that you round a bit here, and maybe you round a bit here, and it does work out to be 1.02. And you're like, oh, I guess it's triangle doesn't exist. Well, it does. You just round it early. Don't round too early. Because especially 2 rounding errors can really mess you up. So we're going to go arcsine of that number should give me, and so I do arcsine of both sides. Alpha is arcsine 0.992 blah 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 blah. And I get alpha is equal to 83.0245. And so I'm going to report that with two significant digits. So 83.02 degrees. How do I get gamma?
Law of Cosines.
You could, or you could say that gamma is equal to 180
yeah.
minus alpha minus. I know, and you're so you want to do the complicated thing because you have this big tool, right? And like a hammer in the hand of a toddler, everything becomes a nail, right? And you have this powerful tool that could do this, or you could just do this, and that's what I'm going to do. I'm going to go 180 minus alpha, which is 83, and again, I'm not rounding this thing. I want to use what my calculator told me, and then I go minus beta was given. That's the 73. So I'm going to go up until I get to my 73.83333333333, and I get something that I didn't get last night. Uh-oh.
I got 23.
You know what I did? Oh wait, no, I didn't do that.
I got 23.14.
That's what I get. Well, I must have messed something up last night. Gamma is equal to 23.1422 degrees. Holding on to two decimal places, that will give me 23.1422. Now let's check that with the law of sines. Because if this works, well, first off, just looking, the biggest angle should pair with the biggest length. Yeah. The next biggest angle should pair with the next biggest length. Yeah. Smallest angle should pair with the smallest length. And now, I might have done something wrong here. 83. It might have been 83.
Oh wait, was it the wrong? There's two 81s. No, that doesn't make sense.
84 goes with beta.
Well, maybe you did the other, because you took arc sine, so couldn't it also have been like a...
It could have been the other sine value, but that doesn't make any sense because that would have been obtuse. Just give me a minute. Give me a minute. Okay, this is what we got to check this, because maybe I did it wrong last night. Let's find out. Since we were given this guy and this guy, right? We were given this guy. We derived this guy. I'm going to use law of sines and just see what it tells me. So sine of the given thing over the thing I derived. So sine of 73.83 repeating over b, which is this, the 84.18277. I'm going to compute that. I get sine of the 73.833, yes. I'm going to divide that by the 84.18, divide by 84.18, blah, 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 blah. Gives me 0.011409. Now, when I do any other pair, it should give us the same thing. So I'm going to try gamma. And I'm going to go sine of 23.1422 stuff over the given 14 and see what I get.
Oh, I got something.
Yeah, I see we messed something up. Divide by 14. Ooh, so yeah, so we messed something up here. Let's see.
It's very close, so it might have been rounding, but I don't think...
Now now one thing we could check is to see if the last one we got works, or this one that we got. So I'm going to go sine alpha, sine of the 8302 and all that, 8302, divide by a, which is 87, does give me this. So something happened. So alpha looks good, gamma does not look good. But how could that be if I did this?
I know.
Alpha and beta. Maybe I just typed that in wrong. 180
Well, I got the same.
minus alpha, which we said was the 83. Okay, this is bugging me. Okay, let's do this. I'll do it the way I did it last night. This shouldn't matter. I imagine I plugged something in wrong somewhere. We're gonna forget that this ever happened. I'll edit this out of the, I'm not gonna edit it out of the thing, but I'm not sure what's going on, but we have to move on. So let's just pretend that we got to this point. Let's pretend we got to this point, and now let's do. So we just got to this point, we don't know these two angles. And I'm going to say, well, it must be true that sine gamma is to C as sine beta is to B, which is the 84.1827. Is that what I got there? That's what I got there. Okay, so this should work. So now, okay, sine gamma equals 14 sine beta over 84.1827, blah, 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 blah. Now let's see what that is. 14 times sine beta is the 73.83. Okay, so I'm going to go up and grab that. Way at the top. Divided by 84.18, blah, blah, blah. Is that what you got?
Yeah.
Okay, there we go. Okay. So then gamma is arcsine of that. 159. So I'm going to go arcsine of that number that I just calculated. That's what I got. Nah. Gamma equals 9.1911.
What did we have to get?
I don't know what happened. I imagine I might have written something wrong when I was over here doing something. I don't know. But this is what I got last night. This one works. Okay. Now we have two angles, right? We know that gamma is 9.19 degrees. Now we could get alpha because alpha is equal to 180 minus beta minus gamma. So we go 180 minus beta was the 73. I go up until I get it. There it is. Minus gamma was the one that I just got, which was 9.19. There it is. Alpha is equal to 96.975. So it's 6 degrees. Keeping it to 2 decimal places, that brings it up to 96.98. So 96.98. This is what I got last night. And then I checked everything with law of sines and everything worked. See how that law of sines came to help us? Like there, I could have said, oh, I just got something wrong, and then we're done. Well, I checked with law of sines and something wasn't right. Okay, so that's one way that you could really check this stuff. And I did this last night. You go this over this, it's the same thing as that over that, or rather sine of that over that, sine of this over that. They're all the same. Nice way to keep yourself from messing something up. I'm not sure what I did. Maybe I'll look at the video and see. But we made the same mistake, which is weird.
Yeah, so it wasn't something in the calculator.
Yeah, I think I may have just written something wrong up here, and we just didn't catch it. I don't know. But this one's good. Trust me on that. Okay, all right. Let me wipe this board. Any quick questions? So we did side angle side. The only thing left to do is a side, side, side. And that is number 12. Number 12. From this section gives us A equals 10, B equals 15, C equals 12. So we need to find alpha, beta, gamma. And I'm going to draw this out because it'll make my life easier if I do. And we'll go make this A equals 10. This one looks longer, so we'll make this B equals 15. This one's C equals 12. And now, what do we do?
Law of cosines? Like,
Law of cosines, yeah. Okay. Give me more. Well, actually, let's do this. So this one's gamma. This one's beta, and this one's alpha.
well, like, 12 squared equals 10 squared plus 15 squared minus 2 times 15 times 10 cosine of gamma.
Okay.
So we could then try to get gamma by itself.
There you go. Right, that's the idea. Is like, in any of these, the only thing that you don't know is whatever that is, or that is, or that is. So that reduces this thing, and like technically you could think of this as like 4 variables. A could be anything, B could be anything, C could be anything, alpha could be anything. In this case, we have 3 of those things. So we could use any one of them. Let's just do the top one first, right? So A squared is equal to B squared plus C squared minus 2BC cosine alpha. Alpha's the thing we don't know. We know all the others, so we just need to get it by itself. And in fact, I'm going to do that ahead of time. I mean, I'm going to, instead of writing all the numbers in, I'm just going to go ahead and rearrange this thing so that I get my A squared minus B squared minus C squared, don't mess that up, is equal to negative 2BC cosine alpha, but I would then divide by the negative 2BC. Don't forget that it's negative. I spent a long time last night going, what's going wrong? How could this possibly give me this answer? Forgot that negative right there. Everybody saw what I did, right? I subtract that to that side, leaving me only this on that side, and then I divide by the negative 2BC right there. Okay? And so, in fact, we could just go ahead and just take another step and say, well then alpha would be arc cos of all this. And if you're comfortable plugging something like this into your calculator, you need to use parentheses very well.
Yeah.
Like your calculator would look like this, but you could do it. It would look like this. Then you would need parentheses for the top, right? All that stuff that's going there, and you go A squared minus B squared minus C squared end parentheses, divide by parentheses
I need
negative
more
2
parentheses if you
B C end parentheses again. If you're comfortable with it, that's how I like to do it. Like, the more times that you put something into a calculator and then try to put it back in, the more chances for whatever. But then, it's kind of hard to write. So, I mean, it's up to you how you want to do this. I'm going to do it all in one fell swoop. I'm going to go ahead and go arc cosine. Now, parentheses. A squared is 10 squared minus B squared is 15 squared minus C squared is 12 squared. End parentheses. Divide by parentheses. Very important that you put parentheses in the denominator. -2 times b is 15 times c is 12. One downside to this method is if you did mess something up, it's harder to find where you messed something up, especially here because you can't get a full readout of this on this calculator, so it's hard to see. But let's see what I got for alpha. That is absolutely what I got for alpha, so I feel good about this. Okay, so this tells me that alpha is equal to 41.649 blah, 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 blah. 41.6497, we'll round. 497 degrees. Okay. All right. Now what? I mean, we could just go through and do that with every single one. But now it seems a little bit easier if we now set up a law of sines to me, because we have 1 in this one, 41, 6 was running with 6.5 degrees. Now we have an opposite. And so we could use law of sines. I personally think that's a little bit easier to do, because I could say sine alpha is to 10. Is to 10 as, let's do sine beta. Sine beta is to b is 15. Beta is the thing I'm looking for, so I could go 15 sine alpha over 10 is equal to sine beta. So then beta must be equal to arc sine of that stuff. I'm just going to toss that in my calculator, see what I get. So, arc sine of, now I have stuff, really don't need parentheses in this case. I could just go 15 times sine, because there's no addition or subtraction in the numerator or denominator, so we don't need to worry about parentheses. This is the same, 15 times sine alpha is the same thing as 15 times, well, I mean, over 10 would be, just whatever. Alpha, we just found, was this. So I'm going to go up and hit it, put it in there. Now, close parentheses on sine, divide by 10. Close parentheses on arc sine, and I get the same thing. Yes, 85.5. Yes. I get beta. Now, if you're not comfortable plugging all this in at once, don't try. Just calculate this number, and then you can have the number. Then you take arc sine of that number. That's totally cool. 85.4593 degrees. 85 point, we'll call it 46 degrees. Last one, should we use law of sines?
180 minus.
Or we could go that gamma is equal to 180 minus alpha minus beta. So that's what I'm going to do. 180, especially since alpha and beta are right there. I can see them on my screen. Super easy to do. So I'm going to go minus alpha is the 41 minus the beta, which is 85. Another nice thing about plugging all of this in at once is that it's all right there. You don't have to go back up and go, oh yeah, that's when I calculated that. That's when I calculated that. That's when it's all just right there. So that's nice. Gamma is equal to, I get 52.891. So there's 52.89 degrees. Is that what I got? Yeah. I did these exactly backwards yesterday. I started with gamma, then I got beta, then I got alpha. We did it absolutely opposite. I got exactly the same stuff. So I feel good about this one, at least. I'm like, I don't know what happened last time. It shouldn't have mattered. Like, it's not like one of those, like, you might take that as a lesson, like, oh, you should do this one first. No, it should have just worked. I don't know what I did. So, everybody get this?
Yeah.
Basically, with law of cosines, the easiest thing is to turn this into a problem that you've seen. The easiest, basically in all of mathematics, take a problem you haven't seen before and turn it into a problem you've seen before. You've done stuff where you're given two angles. You know what to do with that now. And so if you could get two angles, you know what to do. Or once you have an angle and an opposite side, law of sines is usually easier to use than anything else. So, yeah, there's that. So that's what your 1 or 3 through, actually 3 is an interesting one. It gives you a setup, it gives you a triangle, and it says what would you do to do this one. It's pretty cool. But then the rest, 5 through 13 odd, are this. Applications, of course. And for your applications, you're going to need a couple things. One of them, which we are not going to talk about today. We're not going to do it all. Your book has a great proof on it. If you're interested, read the proof in the book. Otherwise, just look at the formula. I know what you do. I know you. No. It's called Heron's formula on page 585. I'm not going to write that up there. This is on you. Heron's formula, page 585. Depending on which applications problems you use, or you choose, sorry, you might have to use Heron's formula. If you choose ones where you don't, then you don't. And you'll never see Heron's formula again. Actually, you might run into it. So, I mean, but I would like for you to at least look at it. But it's very useful in certain situations, though, I mean, whatever. There's a cool proof. You can look over that. We don't need to go over it. What we do need to do is this. What is the area of a triangle? You guys should know this. How do I find the area of a triangle? It's what?
Base times height divided by 2.
Divided by 2. Or, like I like to say it, it's 1/2 the base times the height. Okay, so let's get that up there. Given a triangle, the area is 1/2 the base times the height.
Because it's just half of a rectangle.
It's half of a rectangle, right? And it actually...
Well, what if it's obtuse?
It's also true in this case.
Oh, yeah.
It's also true here, but in this case, your height is that right there. Because you take half of that guy. It does happen to work. We're not going to go into that. But it's... and I've never seen... Well, who cares? Okay. It's 1/2 the base times the height. So we're going to do this a couple different ways. One, we're going to take just any old triangle, and we're going to say, we're going to call this alpha, beta, there's beta, there's gamma, there's alpha. Now, this is just some triangle, okay? And this would be A, this would be B, there to there, be B, this would be C. It's some triangle that's floating out in space, and I grabbed it and oriented it so that alpha's right there. I could have grabbed it and oriented it so that gamma was right there, or whatever, right? But I chose to do it this way. Okay. The height that we're looking for, right? So, and then again, right, what we're trying to do is find the area of this triangle, okay? And so we need the big B for base, and we need the big H for height. The big H for height is this right here. That's H. The big B for base, turns out to just be this guy right there. It turns out to actually be the little b for base, okay? So, right? That's the base. If you were given this right here, and somebody said that's 10 and that's 12, you would go 1/2 10 times 12, right? And so, in this case, the big B is actually the little b. Now we just need H. Now, I'm suggesting something by drawing coordinates there and putting alpha where I've put it. How could we get H?
Sine of H over C.
Yeah, sine of what is what?
Sine of alpha is H over C.
Sine of alpha is H over what?
C.
C. Okay. So that H is what?
C alpha. C times sine alpha.
C times sine alpha is equal to h. Well, there it is. We'll just take that and plug it in, and we get C times sine alpha. That's the area of that triangle. Notice what happened. It's 1/2. Given this angle here, it's 1/2 this side, the two sides that are, as in like the side angle side thing, it's the two sides that enclose that angle are the ones that you use right there.
Okay.
So here's a question. Suppose I had sine, or suppose that I knew what gamma was. What do you think the formula would be? A equals 1/2 something, something, something.
AB sine of alpha. I mean, of gamma.
AB sine gamma. And then we could do that, right? If you imagine, if I just flip this over, I call this gamma now. This would be alpha. Everybody saw what I did? I took my original triangle, I flipped it over, and now gamma is opposite C, alpha is opposite A. B is still my base, right?
Yeah.
And now, when I go to do sine gamma, I get H over A. H over A, so that A sine gamma is equal to H. And so I plug that in and I get this guy right here. What do you think it would be for beta?
I have no idea. 1/2 A.
1/2.
AC sine of beta.
And that's true. Now let's do that one, because this is what I was going to say about when you see the proofs in the book, they use an obtuse angle, and yeah, indeed, and in every case, these are all true, right? I think we've pretty much proved this one. This one, it's the same thing because it's like the way I've drawn it. Those are that both alpha and gamma are about the same, right? So it should be suggestive to you. But now let's say that beta is obtuse, and you might be saying, does it just work that way? That it's the opposite? If you know beta, then you use beta, and then you just use these these that are on the opposite that are on the adjacent sides of that angle. You sure about that? I mean, I could see how it works for this because they're both acute. I see how it works for that because we did it. But what about this? So this is what your book does. So I'm going to draw beta being obtuse. There's beta. And now we'll call this one, say, alpha. And we'll call this one, say, gamma. Gamma makes that length right here, from here to here, C. Right? Gamma's opposite from C. Alpha is opposite from A. Now, what we need is the height and the base. Well, we know the base. The base is this right here. That's my big B, my base. So I know that the area is 1/2 the big base times the big height. The big base, in this case, just happens to be C. Now we need H.
Oh, it's... Oh, wait, no.
So remember how when we defined the trig functions for angles bigger than 90. We did this on the unit circle, right? And we said if your angle, let's call it theta, is bigger than 90, then all sine and cosine are just the coordinates on the unit circle, assuming that this radius is 1, right? And so this coordinate right here is just whatever cosine theta is, right? This coordinate, in other words, that height right there is just whatever sine theta is. And you'll notice that whenever you're in the first two quadrants, sine is always positive. Sine just comes up and does that. Well, look at what's going on here. Beta, you could imagine that if A were 1, then this point would be on the unit circle, right? So if this were here, you'd be tracing out on the unit circle right there, and whatever that height is would be whatever the value of sine beta is, assuming that A was. And then we did this a little bit differently, right? We said, like, well, if that's some radius r, if it's not 1, then you could find it by going r sine theta or whatever. Or we said all you got to do is find the coordinate and divide by r, right?
Yeah.
Or you could think about it as shrink that guy down to a unit circle by dividing by the radius. In any case, however you want to think about it, it's true that sine beta is equal to the height divided by the radius. And just to really drive that point home, right, let's just say that we had some circle here, and it had a radius of A. Okay, so it comes up to here to A. So this is kind of what I'm thinking about. There's that guy. He has a radius of A. From there to there is A. And we said, there's some angle beta. Well, if I shrank this thing down, right? If I shrank it down, I would need to divide this by A, right? So divide everybody through by A. And so if you have this coordinate, whatever it is here, there's your height. That's the height you're looking for. That's the h that we're looking for, right? It would have that coordinate h. But then if we took this and shrank it down, we would need to multiply everybody through by 1 over A to shrink this down to a unit circle of length 1. That would have to be divided by A. That would have to be divided by A, and so on and so forth. The radius would have to be divided by A. And then H, that point up there, would need to be divided by A, putting you at the point H over A. And now, beta, still the same angle measure. Now he's on the unit circle, and that point, that height, it would be whatever it is here, the x value, comma, H over A. But that's exactly what these are. That guy is sine beta. This guy is cosine beta. And so sine beta is H over A. If sine beta is H over A, then H is equal to A sine beta. Which I could replace in here. We have the B, which is C. The H is A sine beta, which I could rewrite in alphabetical order to get my AC sine beta. And so, yeah, they all work in every single case. Doesn't matter if it's obtuse. Doesn't matter if it's acute. In every single case, to find the area of a triangle given only one of its angles, if you know the sides that are adjacent to that angle, so you're in the side angle side setup, then you could find the area.